Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last time, where we were examining how the mutual inductance between the stator and the rotor varies with respect to the rotor position angle. And we had used some of these diagrams to show that as the rotor rotates, the mutual inductance between the stator and the rotor will be a cosine of this rotor position angle, which can be said to be the angle between the axis of the stator and the axis of the rotor, that is, axis of the rotor and the axis of the stator, or could be the angle between the stator flux and the rotor flux. The reason is because the stator flux and the rotor flux will always be perpendicular to the axis of the stator and the rotor respectively. So, due to this, we had been able to come up with this fairly convenient equation which says that this mutual inductance, which is in this electrical equation model, is now dependent on the theta m, and not only is it dependent on the theta m, this dependence is a cosine functionality, right? So if we can express it in terms of a certain maximum, and that maximum is when the fluxes are aligned, in that case, with respect to this maximum mutual inductance, the mutual inductance at any other arbitrary angle is the cosine of that rotor position angle with respect to the maximum. So now the question then arises, we can use this for either of them. So for example, just to complete the discussion, we can come back here. Let me just get rid of these diagrams because we don't need them now. And we can repeat this exact same argument for the rotor as well. So this is what I'm going to do in this lecture, and I'm going to also briefly start talking about the idea of the magnet, or rather the force produced due to the magnetic field. So as before I start the lecture, a little bit of brief background, that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses which you can access on my own website, which is pythonpowerelectronics.com. So this is the home page of the project, and here on the top 4 buttons will take you to the most important links in the page. So if you want to go to the courses, you can click on this button Learn, and this will take you to the list of courses which I have as of now. So currently I have 5 courses. The very first course is Simulating Power Electronic Circuits using Python. And in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the signal package within SciPy to analyze and design filters for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components such as inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python Control package to design and analyze controllers for power engineering applications with the specific case of a single phase inverter connected to a single phase grid. The very last course I have is called Why Specialize in Power Electronics, and this is a free course targeted towards either junior undergraduate students or even high school students to tell them about the challenges and opportunities available in power electronics so that they may choose power electronics as their domain of specialization. So all these courses are available on 2 platforms, which is Decibels Labs and Udemy, and if you click on any of these buttons, it will take you to the link for the course. The link of this page is provided in the description of this video, so if you're interested, please do check it out. So with this, I will return back to the lecture. So returning back to this flux diagram, where we used last time to describe how the stator flux, or rather the flux produced when the stator is excited by a current, can be associated with the rotor and how we can consider this linkage. So we had used several diagrams and we found out that we had to consider, or rather describe, or rather assume that the rotor was energized and assume a certain flux that produced by the rotor and find out what is a projection of the stator flux on the rotor flux. Now, in this lecture, I'm going to reverse the argument and ask the question, what happens if the rotor was excited and how would this rotor flux be linking with the stator. So let's say, for example, in this case, we have the rotor in this particular position, that is, it has a certain angle. So for example, if I were to say that this is the stator axis, so if this was the stator axis, again it's not exactly passing through, but doesn't matter, assume it is, and I realize now that this is not aligned. Let me just align it. Let me delete this and draw another line. So this now passes through the center at least. So we now have two axes which are bisecting, or rather intersecting through almost the same point, right? So if this was the rotor axis and this is the stator axis, then this is an angle. There is an angle made between them. This angle made between the rotor axis and the stator axis is the rotor position angle. And this rotor position angle we have already talked about is this theta m. And this theta m is the integral of the speed with respect to time. So as the rotor rotates with a certain speed omega m, angular speed omega m, it will produce a certain rotor position angle at different times. So coming back here, as this rotor rotates, this rotor position angle will increase. It may accelerate, it may decelerate, it may stop altogether. We don't know. So if I were to say that this is the rotor position angle, let me draw it here. This is the rotor position angle. Okay. Now, the question then arises, if now I reverse the argument and say that this rotor was excited, and we don't care about the excitation of the stator. So we don't care about the stator flux that much. What we care about is the flux produced by the rotor and how it links with the stator. So then the question we must ask is, what is the flux produced by this rotor? So let us assume a certain direction of current for this rotor. Let's say that the current flowing into this upper slot is moving into the page, and the current moving in this lower slot is moving out of the page. So we can use right hand thumb rule, and we find that the flux lines are concentric lines, and for this upper slot they are in the clockwise direction, whereas for the lower slot they are in the counterclockwise direction, right? And a simple right hand thumb rule will verify this. So now that we know this, in exactly the same way for the stator flux, we can come up with one single vector for the rotor flux. So let us do so. So we can draw it in this manner. Think this is okay. I'm trying to make it pass through the same point. Yeah, I think this is reasonable. And let me just draw an arrow. This is an arrow, right? So this is because we have chosen the current direction in that particular manner, that is moving into the slot in this page, into the page in this slot, and out of the page in this slot. Now, since we have a certain rotor position angle theta m between the stator axis and the rotor axis, there will be this exact same angle theta m between the stator flux and the rotor flux, right? So we can draw that here as well. This is the angle. So the question then arises, what will be the linkage of this rotor flux with the stator, right? That is, as this rotor rotates and produces a rotor flux, this rotor flux will also be rotating because this rotor is rotating, and the rotor flux will always be perpendicular to the rotor axis. So, which means for different positions, this rotor flux will have different linkages with the stator. The reason is, in exactly the same way as we did in the previous lecture, we must ask this question: what will be the projection of this rotor flux on this stator flux? Because this projection would be the actual flux that is linking with the stator. So, as always, we can see it is quite obvious that this rotor flux multiplied by cos of this rotor position angle theta m is this stator flux, is the flux which links with the stator. So if I were to just remove this for now, and I just draw a horizontal line, this horizontal line means that this is this is the direction in which the stator flux flows, then in that case, this projection of the rotor flux on this horizontal line will be the flux linking with the stator. And it is quite obvious that at certain positions, for example, if this rotor axis were vertical, then in that case, the linkage is maximum, because in that case, the rotor flux is horizontal, the angle is 0, and therefore the linkage is maximum. Similarly, this rotor could also be in a direction in such a manner that this rotor flux were to be exactly opposite to the stator flux. In that case, the linkage is maximum, but in the negative manner, negative sense. And if this rotor flux were rotor position were horizontal, then in that case the flux is in the vertical direction, and therefore the linkage is minimal. Why? Because the projection of a vertical line on a horizontal line is 0. Cos of 90 degrees is 0. So here again we have seen that we can use exactly the same logic as we did in the previous lecture, and we can say that this mutual inductance between the rotor and the stator has also a cosine relationship as did with the stator and the rotor. So the mutual inductance between the stator, or rather mutual inductance caused because of the excitation of the stator due to the flux linking with the rotor, has a cosine relationship, and so does the mutual inductance because if the rotor is excited and we are calculating the linkage with the stator. So they are mutual. Of course, there may be cases where these are in certain, not all magnetic systems are completely mutual. Sometimes there are differences, but in a vast number of cases, when we say that one mutual inductance has a certain functionality, the other mutual inductance also has a similar functionality. So in this equation, we can say that both of these mutual inductances have this same cosine relationship with a certain maximum. We can calculate the maximum for the stator and rotor, and we can calculate the maximum for the rotor and stator as well, right? However, as you can already see in this case, it is reflexive, which means in both cases it is the same mutual inductance that we are talking about, right? So now that we are here, the question now arises is, we have now said that this mutual inductance is a cosine of this angle. And because it is a cosine of this angle, we have now linked this electrical equations with this mechanical equation, which is calculating this rotor position angle as an integral of the speed. The next thing we need to know is we need to find out an equation for this theta m with respect to the torque, because we need to know how theta m changes. Right now theta m is some mysterious angle, but it's not a mysterious angle. And for that we have another equation. Since this lecture has already gotten pretty long, I will just briefly touch upon this. But what we need is an equation to generate this theta m. So this theta m has to be a function of something, right? So now the question then arises, what is theta m? Theta m is the angular position angle as a rotor position angle. Now this rotor position angle is very similar to the actual displacement. Okay, because this is a rotational machine. A rotational machine is similar to an actual linear machine where the movement is in terms of linear displacement. Here this is a rotation machine, and therefore we are talking about angular rotation and rotor position angle. So to be able to calculate this equation, we go back to our old Newton's equation, which is force into mass into acceleration. This is the linear law. Right? Force into mass into acceleration is the linear law. What we will use instead is torque is equal to G multiplied by alpha. Okay, I'll just write alpha. Actually, it's not alpha. What do I call it? Alpha is probably a displacement. I guess we can call it alpha for now. I can't think of better. But this alpha is the angular acceleration, right? Let me call this angular acceleration. So alpha being the angular acceleration is equal to d of omega m divided by dt. That is, it is the rate of change of speed with respect to time. And Therefore, we now have an equation for this. So we can now say that this J alpha is equal to d omega m divided by dt. So this equation of torque will now produce a certain speed. Right? We can say that this d omega m by dt, or you can just maybe write it here, omega m is equal to the integral of t divided by j dt with respect to time. So this torque divided by this moment of inertia, j is the moment of inertia, I should probably write it here, j is the moment of inertia, wrong spelling, inertia is the moment of inertia, then in that case omega m is the integral of the torque divided by the moment of inertia with respect to time. And once we know the speed, we know the rotor position angle, which is the integral of the speed itself. So you see, now all these equations are coming together. Now the question then arises, what is this torque? Now this torque is this difference between these two torques, which is the mechanical torque and the electrical torque. Now here we will talk, I will stop this lecture because it's getting pretty long and I want to now dedicate some amount of time to this in the next few lectures. But the next lecture we will talk about what is this mechanical torque, what is the electrical torque, and how this all puts together. But what is important is now we have been able to bring in the mechanical component into our electrical equations, and we now have also an equation for determining the rotor position with respect to the torque that is being produced by the motor. So in the next lecture we will talk about how this equation will bring in this mechanical torque and electrical torque, and what is this electrical torque and how is that linked with these electrical equations. So if you have any doubts about what I talked about, let me know in the comments or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with this same description and bring in some more details into this mathematical model. Thank you so much for watching and see you soon. Goodbye for now.